Well, welcome back. This is part 5 in our series looking at advanced higher physics past papers, and this time it's the turn of gravitation. So we're possibly going to be looking at gravitational potential or potential energy, and in fact any calculations that involve big G, Newton's universal gravitational constant. So let's use Mr. Davies' interactive PDF and we'll pick a couple of questions here. So firstly we'll have a look at 2019 question 5 and then 2022 question 4. So let's jump straight in. 2019 question 5. Now the gravitation questions usually come after all the rotational dynamic stuff. So here we go with question 5. Juno is a spacecraft with a mission to survey Jupiter and it's in an elliptical orbit around Jupiter. And the gravitational potential at point A in the orbit is minus 1.7 times 10 to the 9 joules per kilogram. And for 1 mark we have to state what's meant by a gravitational potential of negative 1.7 times 10 to the 9 joules per kilogram. So we have to specifically mention that number in our answer. And so what we're going to say then is that 1.7 times 10 to the 9 joules of energy is required to move 1 kilogram of mass, or a unit mass, from that point to infinity. That's a kind of bog standard definition question, but make sure you refer to the value in the question and that it's a unit mass that you're moving between those 2 points. Part B. At point B, Juno is 1.69 times 10 to the 8 metres from the centre of Jupiter, and we have to calculate the gravitational potential at point B. So straight to your relationship sheet, and we're looking for the gravitational potential relationship. And there it's there. V equals minus gm over r, where m is the mass of Jupiter. Now big G is minus 6.67 times 10 to the minus 11, but where will we find the mass of Jupiter? It's not in the question, so the only other place it can be is in the data sheet, and it's not usually in the data sheet, but remember the data sheet changes from year to year depending on what questions are in the paper, and there it is, the mass of Jupiter. It's 1.9 times 10 to the 27 kilograms, so let's sub that in there, and we have to work out what the gravitational potential is at point B, and point B is at 1.69 times 10 to the 8 metres from the centre of Jupiter. So that is our R value. And then if you do that on your calculator, that gives you an answer of minus 7.5 times 10 to the 8 joules. Remember, gravitational potential is always negative. Don't forget to sub in your negative signs. And there's the SQA MIs, and it's a bog standard 3 mark calculation there. Watch your rounding. And part C, the mass of Juno is 1.6 times 10 to 3 kilograms. Determine the change in gravitational potential energy of Juno when it moves from point A to point B. Well, we know what the gravitational potential is at both of those points, so let's write them down first. The gravitational potential at point A was given in the question is negative 1.7 times 10 to the 9 joules per kilogram. And we've worked it out at point B, it's minus 7.5, and watch your power here, it's minus 7.5 times 10 to the 8 joules per kilogram. Let's just check that. Yep, minus 7.5 times 10 to the power of 8. And to get the change in gravitational potential, remember it's the final point minus the initial point. So it's negative 7.5 times 10 to the 8 minus negative 1.7 times 10 to the power of 9. And if you do that on your calculator, you'll get an answer of positive 9.5 times 10 to the 8 joules per kilogram. And it's a positive change because the little spacecraft has moved further away from Jupiter. Watch your signs there. Now we haven't answered the question yet because the question says determine the change in gravitational potential energy of Juno. Well, there's another wee relationship that's going to be useful here, and that is that the gravitational potential energy of an object is equal to the gravitational potential at the location that it's at times the mass of the object. And we're going to use the form of that relationship where delta EP is equal to delta V times m. So 9.5 times 10 to the 8, that was the change in gravitational potential, times the mass of Juno, which was 1.6 times 10 to the 3, gives us a change in gravitational potential energy of 1.5 times 10 to the 12 joules. That's pretty tricky. Let's have a look at the marking instructions. So it's 1 mark for finding out the change in gravitational potential, 1 mark for the relationship, 1 mark for subbing in, and 1 for the final answer with the correct units. And on the right hand side there, you could alternatively have worked out the potential energy of Juno at both locations, and then the difference between those two potential energies would give you the same answer. Pretty tricky though. Right, let's have a look at another paper and see how that compares. We'll have a look at the 2022 paper, and this time it's question 4. So similar idea here, this time though it's a satellite that's orbiting the Earth in a low Earth orbit. We know the mass of the satellite, and it's 312 kilometres above the surface of the Earth as shown in the diagram. And we have to show that the gravitational potential energy of the satellite in this orbit is negative 1.4 times 10 to the 11 joules. So we're going to need the gravitational potential energy equation. EP equals minus gmm over r, where r is the radius of the orbit. And for that we're going to need to add the height of the satellite above the Earth's surface plus the Earth's radius. And big M is the mass of the Earth. So we'll need quite a few things off the datasheet here. We'll need the radius of the Earth, the mass of the Earth, and big G as well, that's on your datasheet, and then we're going to sub them all in here. So that'll be minus 6.67 times 10 to the minus 11 times the mass of the Earth, which is 6 times 10 to the 24. And small m is the mass of the satellite, which was 2.3 times 10 to the 3, and that's all over the radius of orbit, which is the height, 312 kilometres, plus the radius of the Earth. And if you do that in your calculator, you'll get an answer of negative 1.4 times 10 to the 11 joules, and that is what we had to show. Because this is a show question, I'm going to be very careful with my relationship. I'm going to add a little p in, subscript p, it should be there for gravitational potential energy, because those markers of the SQA can be real sticklers for detail, so make sure you show everything explicitly in a show question. Let's look at the MIs. 1 mark for the relationship, 1 mark for all substitutions. Nothing for the final answer, but it does have to be there with the correct unit. Okay, on we go. Part B, the satellite's got an orbital period of 90.7 minutes, and we have to determine the speed of the satellite in this orbit. Well, we've got a time and we've got a radius, so we can work out the circumference of this circular orbit. So we can use speed equals distance over time. The distance will be 2 pi r, and remember the radius will be the height of the orbit above the Earth's surface plus the radius of the Earth, and the time will be the 90.7 minutes times 60 seconds, and that will give us our answer in meters per second of 7750 meters per second. That's rounded to 3 significant figures. Let's have a look at the MIs. Bog standard 3 marker there. Tricky because remember you've got to add on the radius of the Earth and convert it to seconds. There's also alternative methods on the right hand side there where you could have used the angular velocity relationships, or you could have equated the central force and the gravitational force, but that looks like far too much work. We'll stick with the easier option. Okay, for part C, what's the total energy of the satellite in this orbit? Well, it will have a combination of gravitational potential energy and kinetic energy. And we can work out how much kinetic energy it has because we've just worked out what its speed is. So EK is a half mv squared. That's a half. The mass of the satellite was 2.3 times 10 to the 3 times the speed squared gives us an answer of 6.9 times 10 to the 10 joules. And then we're adding the kinetic energy and the potential energy together. We worked out the potential energy earlier. It was negative 1.4 times 10 to the 11 joules. And then if you do that on your calculator, you'll get a final answer of negative 7.1 times 10 to the 10 joules. And remember, the total energy of an object in orbit will still be negative. There's the MIs. 1 mark for adding the two energies together, 1 for subbing everything in, and 1 for the final answer. Don't forget that negative sign. You could also have got the marks here if you look at the right hand side if you knew that the total energy of a satellite in orbit is minus GMM over 2R. That relationship's not on your relationship sheet, but some folks do remember that. Gives you a slightly different answer as well because we've not got a V in the calculation. There's no rounding in the speed in there. Okay, final bit, part D. Suggest why a satellite in a low altitude orbit will lose energy at a greater rate than a similar satellite in a high altitude orbit. Well, there will be atmospheric drag due to the Earth's atmosphere, and that will be greater at a lower orbit. 1 mark. There's the MIs. Greater drag or friction from the atmosphere. Don't be tempted just to write friction there. If you just write friction or drag on its own, you won't get the mark. You have to say it's friction from the Earth's atmosphere. And that wasn't the last bit. There's another part, 4 part E. The gravitational fields of the Earth and the Moon create 5 Lagrangian points. I hope I pronounced that right. A Lagrangian point is a position near 2 large bodies in orbit around each other, where a smaller object, such as a satellite, will remain in a fixed position relative to both orbiting bodies. Whew. What's that all about? I think I'm going to look this up, see if I can get a picture. There we go. Don't know if that helps or not, but that's the 5 Lagrangian points around the Earth. They're kind of special points where you can put satellites in orbit. Very stable positions. Anyway, the distance r from the centre of the Moon to one of the Lagrangian points can be calculated using this relationship, and you've never seen that relationship before. It's an unfamiliar relationship, and with this type of question, all you've got to do is find the numbers and put them in and work out what r is. We have to calculate small r there. So let's write it down and then figure out all the numbers we need to sub in here. So capital R is the mean radius of the Moon's orbit. M1 is the mass of the Earth and M2 is the mass of the Moon. And you'll find all of them on the data sheet. So, to save me scrolling back and forward, there's a wee data sheet there, and there's everything we need. So capital R is the mean radius of the Moon's orbit. It's 3.84 times 10 to the 8. M2 is the mass of the Moon. It's 7.3 times 10 to 22, and then 3 times the mass of the Earth. Mass of the Earth, 6 times 10 to 24. And then it's just a case of plugging all that into your calculator and working out r cubed first. So that's 2.3 times 10 to 23, and then cube root it. Gives you your final answer of 6.1 times 10 to the 7 metres. Let's check that on the MIs. It's only 2 marks, so 1 mark for subbing everything in and 1 mark for the final answer. There is no mark for working out r cubed. In fact, it's not even shown on the MIs. I'd be tempted to rub that out. Don't even show that line. That's the line you could go wrong with intermediate rounding or incorrect rounding. So, get into the habit of relationship, substitution, final answer with the correct unit. So, 2 very similar questions there. Spent a lot of time looking up the data sheet, and remember to take care with your positive and negative signs. That's it for this one. In the next one, we're going to look at general relativity. That will probably include things like escape velocity and Schwarzschild radius, black holes, space-time diagrams, and Einstein's happiest thought, the equivalence principle. But we'll see you in the next one.